Okay. Good afternoon, everyone. Today we have the honor to have Professor Jiashun Jin from Carnegie Mellon University as our webinar speaker. Jiashun is a professor from Department of Statistics and Data Science and affiliated professor of machine learning. Professor Jin's earlier work was on large-scale multiple testing, focusing on the development of Tukey's higher criticism and practical false discovery rate controlling methods. His more recent interest is on the analysis of social networks and test documents, focusing on the development of the score normalization and on cycle count methods. He has also led a team collecting and analyzing a high-quality, large-scale data set on the publications of statisticians. Professor Jin is an elected IMS Fellow and ASA Fellow. He has delivered the highly selective IMS Medallion Lecture in 2015 and IMS Annals of Applied Statistics Lecture in 2016. He is also the recipient of the IMS Treaty Award and ICCM Distinguished Paper Award. Without further ado, let's welcome Professor Jin and of his talk, The Statistics Triangle.
Okay, thanks a lot. Thanks Zhihua for inviting me to present to give this me the opportunity to present some of my recent work. I'm really glad to hear to discuss the statistical triangle, and this is in collaboration with Hong Shengji, Tracy Ko, Wan Shanli, and Shengming Lu. Okay, why cannot move? Okay, okay, so recently our group we have collected a large-scale data set on the publications of statisticians. We call this data set multi-attribute data set on statisticians, or the MADStat. Basically, we have in this data set we have collected the following information. The first part, two parts of information. The first part is so-called bib text information for 83,000 pages in 36 journals spanning 41 years from 1975 to 2015. And in the bib text, you have the title, author affiliation, abstract, references, keywords, and MSC subject classification, all this information. As you can see, because the main content of the paper is very long, so we do not download. But aside from that, everything else is downloaded. And the second part of the dataset, information of the dataset is that the citation counts. Like within the scope of this 87,000 papers, we actually have downloaded the citation information of which paper cite which. For example, in paper I, cite paper J. Okay, then we have a count there. Okay, so compared to there are several data set of the similar kind in the literature. A lot of them in the machine learning, a lot of them in the social science or library science. But what is special about this statistics is multivariate. For example, you may see citation data elsewhere, but for this data set, we not only have the citation, but we also have author information, author information, journal information, time information, and we also have the text document. For example, you can use the paper abstract and the references as the paper the text document. Okay. Another noteworthy feature is that compared to Scholar Google, Scholar Google, you can easily access the citation information of a given paper, but if you want to access a large volume papers, the citation information is actually not available to you. And the second of all, the Google Scholar, the citation information is kind of noisy. Okay, so for our data set, we not only have this data set downloaded, but we have to spend 2 years to clean the data set. So it makes the data set more high quality. Okay, so in summary, we have spent a long time, 2 or 3 years, to collect and clean the data set and annotate the data set. But the good news to everybody here is that the data set is made freely available. So if you want to access the data set, you can either go to Tracy Ko, one of the collaborators, okay, of this project here, or the journal website. Okay, both of these journal websites, they have the data set. It's freely available to everybody. There are many problems you can study. You can refer to our papers, like for example, you can study the co-authorship community tree, journal ranking, citation prediction, so on and so forth. For the interest of time, today we are going to focus on 3 problems. These 3 problems are intertwined with each other. Like the first one is, what are the representative areas in statistics? By saying representative areas here, we mean the primary research areas, like the big areas in statistics. Of course, each primary research area they might further be divided into sub-areas. Okay. And then how to estimate the research impacts of interest of a given author, such as me. And how do the author's impact interest evolve over time? Okay, so this is the 3 problems we're interested in today. Okay, if you want to learn more, you can refer to the paper. Okay, the tool we are going to use, we're going to build 21 Scite network. The Scite network use both the BibTeX data, okay, both use BibTeX data like references, and also use the citation information. You know this, if you want to brute force build a citation network, it's very inconvenient to analyze it because it's not symmetrical, and so far the method, modeling method and series not very ready yet. Okay, so we consider the so-called Scite network. Scite network is symmetrical, but it's not the simple symmetrization of the citation network. So the Scite network is defined as follows. You given 2 authors, okay, here, look at it here. For example, you have paper 1 and paper 2, okay? So this is both co-cited or cited simultaneously by paper X. When this happens, we think there's a age between paper 1 and paper 2, okay? And then they have been co-cited for one occurrence. Of course, an author, they can have many papers, right? If 2 authors, they have been co-cited by another author, we say they have age. So in this Scite networks, the load are actually not paper, but the authors, okay? We have constructed 21 Scite networks as follows. According to these 21 different time windows. The time windows are not evenly divided. The reason is because in the 1990s, you have less citations compared to the more recent years, like 2015. Okay, we are going to construct. We are going to use the first Scite network as a static network and to as a benchmark to study research interest. And we're also going to study dynamic networks, like how this network evolve over time, especially the research interest, how research interest of individual author evolve over time. For the interest of time, we're going to spend most of the time on the first part, okay, and we're also going to discuss a little bit on the second part, okay. In the next slide, I'm going to discuss the first network, the first Scite network, this one, the benchmark one, from 1991 to the 2000 in more detail, okay. After that, we are going to see, you are going to see a statistic triangle, a research map, and so on and so forth. You may find that our results do not fit well with some of your knowledge about the statistics community, okay. When that happens, let me remind you that the first Scite network is in 1991 to 2000. It's not recent years, okay. So the first Scite network from 1991 to 2000 built as follows, and other Scite network is built similarly. Basically, if you have 2 authors, fixed 2 authors, these 2 authors may have many counts being co-cited. For example, you and Zhihua and I being cited by other authors for a total of, let's say, 80 times, okay, 80 times, okay. Then between she and me, there's a weighted age with the weight is 80, okay. So this is the original network. Then we are going to remove all these authors with total weight smaller than 80. For example, Zhihua and I being co-cited for 80 times, and Trace and I being co-cited for 100 times. So you plus 80 and 100 and something else together, that's my total weights, okay. If my total weight is too small, okay, I'm going to be removed, okay. And there's also age weight. If age, okay, for example, if Trace and me have age, if this weight is bigger than 2, we retain. If it's smaller than 2, it's removed. After that, you will have like a, okay, you will have like a trimmed late work. Now, use this late work to build unweighted late work. If the age weight is retained, you make it 1. If it's not retained, make it 0. Now you have a binary unweighted symmetric late work. This is the Sci late work. We take the GN component for the first one, for the second one, for the 21st one, okay, for the 21st one. So for all these 21 networks, we take the, they may have different number of nodes. We take the intersection. So this intersection of 2,830 nodes are the common set of nodes in all these 21 networks. We call them the most active authors in these data sets. Okay, so far for the Sci late work. Our purpose is we're going to first use this late work to identify primary research areas in statistics and going to estimate research interest for individual authors. The second one is we're going to use it as a benchmark for studying all 21 Sci late works, and especially for studying how research interests of a given author evolve over time. Okay. In his Fisher lectures, I think the 1990s, Efron's Fisher lecture, he pointed out there's a philosophical triangle in the statistics. For example, in this triangle, we have 3 main philosophies: Bayesian, frequencies, and Fisherian. This is due to R. Fisher. Okay. Efron's point is that, for example, you take EM algorithm here. So EM algorithm, you may think it as a convex linear combination of 3 different philosophies. Okay, so therefore this is referred to as the philosophical triangle. Okay, as an overview to our result, we also discover a statistical triangle. Our triangle is reminiscent of Efron's triangle, but it's based on the data set we just mentioned. Okay, so we're going to use this statistical triangle as a benchmark late work, and we use the benchmark late work, we have find the triangle. Okay, now for all others Sci late work, we also find the triangle. Okay, now different triangle you may not align well. So we are going to align different triangles well so that the research interest estimated for different author over different time window is aligned. So in collecting them, that becomes the research interest of an individual author. Okay, we are going to discuss all this. Okay. I'm going to spend 3 slides on the model and then 7 slides on the methods. Okay, we try to be as simple as possible. And then save more time on the data set part. Okay. We're going to use the so-called degree corrected mixed membership model for the research interest and impact. Okay. Here N, we give an N by N adjacency matrix of the Sci late work. Let's focus on first Sci late work for now. Okay. Adjacency matrix is very simple. If there's age between node I and j, then Aij is 1, otherwise 0. Okay. If I and j are equal, okay, we always regard them as 0. Okay, we do not count self ages, the age between an author and himself or herself. Okay, so therefore, this matrix first is symmetrical. Second, the diagonal entries on the main diagonal are always 0. Okay. Now, we assume there are K perceivable communities. We do not know them, okay? We do not know K, and we do not know the communities. So communities in networks kind of refers to tightly woven a group of nodes which have more edges between than across different community, okay? Just like clusters in the unsupervised learning, clusters is like intuitive, but it's pretty hard to define rigorously. Okay, so community is actually just a cluster network. Okay, you may think each of these communities is the primary research areas. For example, Bayesian, long parametric, that's the community. Okay, now for the same case here, we assume for a rank K model, a rank K matrix omega, which is okay. The upper triangles of A are independent Bernoulli's and omega ij equals to the probability of Aij equals to 1. Okay, so you can imagine, okay, so this matrix, okay, It's non-negative, it's symmetrical. And we also assume it for rank is K. Why? Because otherwise this is over-parameterized, okay? We assume is a rank K, then this is really reduce a lot of free parameters. It makes this model estimate, it's possible to estimate, okay? We can always decompose A as two components. One is a Bernoulli probability, which is the non-stochastic part, and the noise part. For example, Wij basically means Aij subtract omega ij. Okay, we have to subtract the diagonal of omega here because diagonal of A is always 0. If you force the diagonals of omega to 0, then it's very hard to make it rank K. Okay, so therefore, you subtract the diagonal of the omega, so therefore is omega has more flexibility, then you can impose a rank K assumption here. Okay, so this is the first layer of modeling. Okay, we have a Bernoulli model, and omega is the Bernoulli probability matrix. Okay, now the next step is how to model omega. There's many approaches. Okay, here today we're going to mention the block model family. The block model family including at least 4 members, maybe more. Okay. And the baby version was proposed in the 1983, okay? And later, it's extended to different directions. And today, we are going to focus on the degree-correct mixed membership models, okay? For all these modeling strategies, we recognize there are 2 very important features of late work. First of all, is the so-called degree heterogeneity and a severe degree heterogeneity. Take the treater, for example. Okay, take the treater, for example, the social network, for example. We always know that Elon Musk has a very high degree, right? And take another person, just a typical person. If you compare their degree, Elon Musk's degree may be much higher than the other person. Okay, so therefore, the first thing, the degree of different nodes are very different. Okay, it can be very different from one node to the other. Now, the second of all is social networks. Typically, they have so-called mixed memberships. The mixed take the CIT network, for example. You're a fixed author, like Jiashun Fan. So his citation may comes from Bayesian, long parametric, and biostatistics, so on and so forth, right? So you cannot say Jiashun is 100% belongs to long parametric, not Bayesian, not biostatic at all, okay? So therefore, this so-called mixed membership means you cannot say every author belongs to exactly one community. Okay, it has different ways on different community. For example, therefore, we are going for each author, we are going to introduce a so-called research interest vector. Okay, so research, for example, if I is Jiashun Fan, then his research interest vector is a k-dimensional vector. And the corresponding entries are the ways he has in different primary areas in statistics. For example, he may have 10% in Bayesian, 80% in long parametric, and 10% in biostatistics. So in that case, capital K is 3, and his research interest vector is a 3-dimensional vector. Okay. So in order to model that, okay, in the baby version of the stochastic block model, we do not model either the severe degree heterogeneity or the mixed membership. If you want to move away from that to model the degree heterogeneity, then the degree corrected block model. If you want to model the mixed membership, you have the mixed membership stochastic block model. If you want to model both, then this is a degree corrected mixed membership model. And for the CIT network, it's clear that we have both. We have to model both. Okay, so therefore, okay, we have this model. Okay. So this omega in this degree corrected mixed membership has 3 layers. First of all, for every node, you use one free parameter to model the degree, and use one k-dimensional vector to model the research interest. And on top of that, we also need a k by k, very small matrix, which to model the baseline citation between different areas. For example, P12 maybe P, okay, the first row, second column may be the citation exchange between a typical Bayesian author and the typical long parametric author. Okay, so that's the P. Okay. Okay, so here is a very simple example what omega looks like. On the left, you can have a diagonal matrix, okay, where the set I is a degree heterogeneity for author I. In the middle, you have a very small matrix. If k equals 2, then it becomes 2 by 2. So this is the baseline citation changes between primary research areas. And here is a very skinny matrix, very, very tall, but very skinny. Each row is an author, and each row represents the mixed membership vector for author I, okay, for the corresponding author. Okay. Now, an important notion is so-called pure nodes. We call node I pure if pi I degenerate and mixed otherwise. Let me ask you a question. What kind of author would be more pure? A fresh PhD or a senior professor? It's clearly that the senior professor is less likely to be a pure node, and the fresh PhD is much more likely to be a pure node, because a pure node means you only have citations from one of these K areas, okay? And a senior professor, they have the, it's very likely to have the research as the citation from different research areas, so therefore it's more mixed, okay? For example, 1, 0, if your pi I is 1, 0, you are pure, and your 0, 1 is also pure. Otherwise, 0.5, 0.5, 0.1, 0.9 is all mixed. Okay, and our primary research, primary goal here is to estimate this blue matrix. Okay, it's a mixed membership matrix. Okay, so the very interesting here is to note that these set I are kind of nuisance parameters if you want to estimate pi I. Okay, let's give an example. So, for example, you can very easily find an author who has a similar set I as mine, but his or her research interest is very different from mine, okay? But at the same time, one of my students, his set I and my set I may be very, very different, but he and mine pi I, his and mine pi I are maybe very similar. This means that, okay, you can be very senior, you can be very high impact, but your set I, your pi I may be very similar to junior faculty. Okay, so all this means, in order to learn pi I, set I is sort of like a nuisance parameter, and in order to estimate pi I, therefore we need to remove the nuisance effect of set I. Okay, and this is done by so-called score normalization. There are many ways to remove the nuisance effect of set I, but it turns out the score has been most effective compared to others. For example, Laplacian. You can use the so-called Laplacian normalization, but it's less effective compared to the score. The idea of score is very simple. Okay, input the adjacency matrix and the number of accumulated K. You obtain the leading eigenvectors. Then you divide the second eigenvector by the first eigenvector entry by entry, and divide the third eigenvector by the first eigenvector entry by entry. So eventually you have like n by k minus 1 matrix entry-wise ratios. Okay, it has been shown that this is actually a very effective way to remove the degree heterogeneity and provide a convenience way to estimate this pi I, and this is our goal. Okay, we're going to estimate pi 1, pi 2 up to pi n. Okay, pi I is a research interest vector for author I. Okay. We're going to spend like 6 more slides to discuss method, and the key is to study the population version R hat. Okay, in the population of R hat, okay, here are the eigenvectors of A. Okay, in the population version, we are going to replace this A by omega. So in the, okay, you replace A by omega, so therefore you let lambda k and cosine k be the case eigenpair of omega, and with a hat, that's the case eigenpair of A. Okay. You similarly, you can divide the case eigenvector of omega by the first eigenvector of omega, that is R. So R would be non-stochastic. It's similar as R hat. Okay. Now the main theorem is the following. Okay. This is R in the population version. Okay. It has n rows. Each row is k minus 1 dimension. Okay. Therefore, if k equals to 3, okay, if k equals to 3, then each row of R is 2 dimension. Okay. Okay, each row of R is 2 dimension. okay, and so on and so forth, okay. Now, if you plot all these rows, you have like thousands of points on the, okay, on the, for example, if k equals 3, then this will be on the plane, okay, the two-dimensional plane. You have thousands of points on the plane. It turns out there's a simplex, which we call the ideal simplex, with vertices v1, v2, and v3, if capital K equals 3, okay? So v1, v2, 3. So Ri falls on one of the vertices if load I is pure, and falls inside the simplex if the load is mixed. Moreover, you can always write this Ri as a convex linear combinations of the k vertices. Okay, if capital K is 3, again, this is 3. Okay, so therefore that will be given to you a three-dimensional weight vector Wi. Okay, you have a point, you have a triangle. Okay, if k equals 3, you have a triangle. Okay, you pick a point, pick a row of R. Okay, you must fall inside the triangle. Then you can write this Ri, small ri, as a convex linear combination of the three vertices, and the weight is a vector, okay? Weight Wi1, Wi2, Wi3, okay? Is that the Wi is weight vector, okay? You can, from the simplex and your Ri, you can easily find that weight. Now, if you this is three-dimensional vector. This is also three-dimensional vector introduced as follows, which only depends on the eigenvalues omega and this vk. This is the vertices. Okay, we just found okay, these vertices. Okay, so if you divide this vector and this vector entry by entry, so this is remains a three-dimensional vector, and this three-dimensional vector turns out is almost pi I just up to a scaling. So therefore, if you take this and renormalize it to have L1 norm being 1, then this is exactly pi. Okay, so this is the main idea. Okay. Any questions? Okay, so let me just repeat this. Okay, in the population version, you can easily find this pi I as follows. First, you obtain the capital R, which has n rows, n the number of authors, and k minus 1. Columns, k is the number of communities. Okay, you plot all these n points. Okay, in the k minus 1 dimension. Okay, you plot all these 1,000 points, for example, in the plane. Okay, then because they form a simplex, using all these points, it's not hard to find the vertices of this triangle. Okay, or the simplex. Vertices of the simplex. Okay, once you have this simplex, you can use Ri to cover this Wi, and once you have this Wi, you can find your pi I. Okay, easily. Okay, so this is the main idea. So of course, this is for the population version. For the real version, you do not have very nice triangle like this. Okay, so every these points is a row of R. Is now will in the real world it's going perturbed or corrupted by noise. So you really do not have this nice simplex. But you can use all this data, all these rows, noise the corruption version of these rows to estimate these vertices. Okay, this is step we call it vertex hunting. The vertex hunting basically just use the rows of R hat. R hat is a real data version. Okay, to estimate the k vertices of the ideal simplex, that's called vertex hunting. Okay, we have many methods. Okay, in a survey paper proposed here. Okay, this is a survey paper. We have many different approaches. Okay, you can check out there. Okay, and so there's another idea is about normalization. So score basically is a post-PCA normalization. You do the PCA first, okay? Then after that, you do normalization. There's other normalization ideas, for example, the Laplacian. You can do the normalization before you do PCA. We call it the pre-PCA normalization. Both approaches can alleviate the effect of the severe degree homogeneity, but the scores must be more successful. But it's slightly better if you just combine both. So that means you do a normalization before you apply PCA, then you do PCA. then you do the score normalization. Okay, so you can combine all these ideas together. Okay, now this becomes the procedure. Okay, first you can do a Laplacian normalization where D is a diagonal matrix with Di is the degree of load I. Okay, so this is a tau. Tau actually is average degree. Okay, so this part is a rigid regression kind of thing. Okay, without this rigid regression, this is a symmetrized Laplacian. With rigid regression, okay, just a regularized Laplacian. Okay, so you obtain this L, you apply the score normalization to it. You use the vertex hunting. Okay, for example here, pick one. Okay, we'll recommend the one. Okay, the one in the paper. Okay, you do the vertex hunting. So you have estimated all the k vertices of the ideal simplex. Then you just mimic the population version, use a simplex structure and Ri hat to compute Wi hat. Okay, then you compute this B1. Okay, this is okay, mimic population version. So finally you have Wi B1 and you can just recover your pi I, estimate your pi I hat, pi I like this. Okay, so this step and this step is very similar to the population version. This step is more complicated than the population version. Okay, but there's a lot of details in the paper. Okay, so and this is a Laplacian. Put all this together, that's the algorithm we are going to use it here. Okay. Okay. Now we have introduced the model, we have introduced the procedure. So okay, now we are going to discuss application to the math stat data. Okay. There's two goals. One goal is we want to estimate the primary research areas. Okay, we can do that by estimate the vertices of ideal simplex. Okay, and also we're going to estimate the research interest of individual author. For example, me or Jianqing Fan or Zhihua here. Okay, so this is two goals. Okay. Now, the second point is a primary research area, like Lampert matrix, they have many sub-areas. How to estimate these sub-areas? Okay, the idea of us is the following. So this is, again, is R hat matrix as before, okay? This has n rows, each row is author, and k minus 1 columns, okay, and k is the number of communities, okay? We are brute force just use the k-means to cluster these to, let's say, 20 different groups, okay? So each of these 20 groups is then regarded as a sub-area, okay? So this is one goal here, two goal here, and third goal here. One goal is identify the primary research area. Another goal is to estimate the research interest of individual author, and the third goal is to, okay, estimate the secondary or the sub-area in statistics, okay? And this one more goal is to estimate, to study how the research interest of an author evolve over time. So that we left the next, okay? Okay, so in order to do all these, we need to figure out K, okay? The number of communities, okay? It takes quite a long time to figure out the K because, you know, K for the real data is not given, but in our procedure, we assume it's a no. Okay, that's a question here. Okay. Yeah, okay. The question actually is about how to select K. This is what we are talking about now. Okay. How to select this K? Okay. So first of all, we plot the scree plot of the Scikit network. Then we try K equal to 2, 3, 4, 5, up to 10. Okay. Now for all these different K, for all this each of these K, we are going to try our mixed score algorithm. Okay, we try it. Okay, then we are going to look at it, look at all those points for close to the one of the vertices. If the row for very close one of the vertices is regarded as the pure nodes, we print out all those rows, especially those with high degrees. with like the top degrees pure nodes. Then based on that, we're using our partial knowledge about the statistical community. We're trying to study those persons' research interests and use those to guess what research area it represents. So eventually we tried for K equals 2, K equals 3, up to K equals 10. After a long time of discussion, we figure out K equals 3 produces most meaningful results. So therefore, that's how we figure out 3, okay? Since K equals 3, the simplex is a triangle, okay? It's triangle. K minus 1 is 2, so the triangle, okay? And also use the printing out the pure nodes kind of approach. We can interpret these 3 primary research interests are actually based biostatistics and long-term metrics, okay? And how to decide the number of sub-areas? We do similarly, okay? We have tried the number of M of 5, 6, 7, up to 20. Then we print out for each of these sub-areas, or each of the clusters, to print out the top author, the high-degree authors. Then we look at them, we print out their names, and then we label each sub-areas. Okay, so eventually we decide 15 clusters may be an appropriate number of sub-areas. Okay, so this is how we decide the number of primary research areas and the number of sub-areas. Okay, so this is the result. Okay, this is the result. So since K equals 3 is a triangle, okay, so these 3 vertices can be interpreted by long-term metric base and biostatistics respectively. Okay. You can also see when we apply the k-means, you have this kind of partition region. This is produced by k-means algorithm. Okay, applied to this matrix. Okay. So this is all the regions identified by k-means. Okay, so we have 15 of them. Okay. Now, third of all, we are going to, for each sub-area, we print out the top 5 authors with the largest degree. Okay, so we print out their names. Okay. Now, this is quite interesting. For example, on these vertices, okay, we find these authors are actually in the area of kernel estimation. Let me remind everybody. So this is based on the scite work in 1991 to 2000. Okay, 1991 to 2000. So kernel estimation is a well-known research area in non-parametric statistics. So the basic goal there is because, you know, a kernel method, they have like a bandwidth. Okay, kernel estimation, kernel estimation is one of the very popular approaches to non-parametric estimation, and a lot of work of this person is trying to send the bandwidth of those kernels. Okay, so because this kind of work, bandwidth selection, their impact is mostly in non-parametric, not too much in base, not too much in biostatistics. They are fall on the corner. Okay, fall on the corner. And this group is also very interesting. This group, if you look at them carefully here, they are actually a whole bunch of physicists. They're not statisticians, they're physicists. Why that happens? Because in the 1990s, there's a hot areas, the Bayesian computation, or you can call them machine learning, early machine learning, or you can call them Monte Carlo Markov chain. Okay, Monte Carlo Markov chain, there's a very important notion called annealing. Annealing in physics terms is like you have a piece of metal, you heat them to like 10,000 degrees. Then you bring the degree down by put the metal in the water. Okay, so that is kind of annealing. So Monte Carlo Markov chain algorithm, by in the 1990s, is the sort of, because to speed up the computing, they're sort of using so-called annealing techniques. So, and in those papers, they have cited the physicists' work, okay? Because these physicists, they may be very high impact and have citation for everywhere in physics, but in the statistics community, their impact mostly comes from a Bayesian side on the Monte Carlo Markov chain. So they are become the pure node here, okay? And of course, here's also, this one is also very interesting, the clinical trial. Clinical trials made high impact in like a cancer study and other areas, but in this data set within this scope, their research impact is mostly on like longitudinal data epidemiology, not too much on non-parametric base. So there becomes the pure nodes here, okay? So this explain why these people fall on the vertices, okay? And move along here, just the wavelet sub-areas. These wavelet sub-areas, for example, they've done in Johnston, okay? So wavelet research area, okay, is interdisciplinary area of statistics, applied math, and electrical engineering. So because they're interdisciplinary, they're kind of sit on the side of the triangle. You move down this way, these are the decision theory. For example, you can have the Larry Brown, okay, admissibility, minimax, all this kind of notion. Move down this road, there's a Bayesian computing, okay, the Bayesian computing is this one. Bayesian computing, you can see Peter Green, Dennis Cook, Luke Tintineri, James Berg, okay, Bayes, okay. This is already explained. And move down here is, it's another group of Bayesian, including one of my, several of my colleagues like Robert Cass, Joseph Cadden, and Larry Wasserman. And this is Adrian Rafferty, is from University of Washington, I think, okay. There's Roberts, okay. Move down this road is another, okay, Bayesian groups. Move down here is actually longitudinal data or the general estimation of equations. For example, you can find Xihong Lin, Lumen Breslow here, and Quinn Liang here. Yes, Scott Ziegler. Okay, so this is well-known figures in general estimation equations. Okay, so move down here is longitudinal data, and move down here is epidemiology, and move down here is survival. Okay, survival. Okay. So in between, you have two of them. Okay, between like 2 and 7. Okay. So this is a very highly influenced group, like Bradley Efron, Robert Schwanny, and they basically do like Ray Carroll. They do like a long parametric, semi-parametric, Lasso and Bootstrap. Okay, and this is a long parametric. This is also like okay, well established figure, well-known figure like Peter Hall, Jianqing Fan, James Merriam, and so on and so forth. So for example, Ray Carroll is kind of on the edge because he's a semi-parametric and long parametric, sort of on the edge of these two. Okay, of these two. Okay, so this is a statistical triangle. It illustrates in statistics there are 3 primary research areas, and you can divide it to a number of sub areas. And for us, we recommend 15 based on this data set. We don't think this 15 is very accurate, but we do think this 3 is pretty accurate. Okay, you may have so time may change. So we now talk about like deep learning, artificial intelligence. But in statistics, these 3 vertices still represent the most important philosophy in statistics, just Bayesian and long parametric. And also, they also have another very important vertices, which is applications in biostatistics, epidemiology, cancer study, biomedical, and so on and so forth. Okay, so the next we're going to spend a few minutes to talk about the dynamic network. Remember that in the very beginning, we have constructed 21 scikit network. So far, we have focused on the first one, the benchmark one. The main point about the dynamic, to start this dynamic network or how this network evolve over time is like this. So for each of these network, because we believe this is statistical triangle still there, which represents 3 primary research areas of statistics, and this would not change significantly over time. So therefore, we have one triangle for network 1, another triangle for network 2, and so on and so forth. We have 21 networks, but each of the triangles is computed using score based on an individual scikit network. They are not aligned well. So in order to start, in order to study something meaningful, we have to align them correctly. So this is the way to align them. Okay, for example, A time T, okay, author I, for example, I is Jianqing Fan. So this is Jianqing's research interest at time window T, okay. So R hat and pi I is closely related. So this is just a line R hat is almost similar to a line pi I, okay. So you align this way, okay. After you align this, you can collecting, this is already aligned, collecting them, okay, so it's a little bit jumpy, so you have a kernel smoothing applied to it, okay. You collecting all these 21 points, okay, then that is the research trajectory for Jianqing Fan, okay.
Professor Jin, there's a question, I think,
okay, sure, okay.
Audience,
sure.
Sorry to interrupt.
Should I read the chat or Q&A?
I think Ina wants to raise the hand. Yeah, you can talk now, Ina.
Okay, sorry, okay. There was an accident.
Oh, no problem. Okay.
Yeah. Okay. Okay. Okay, good. Okay, so that will be the trajectory. Okay, to show the trajectory, let's go back a little bit to this figure. So please pay attention to this yellow box. Okay, to this yellow dashed box. For visualization, I'm going to zoom in to this yellow box. Okay, zoom in to this yellow box. Okay, so therefore this figure is a zoom in of this yellow box. Okay, now, okay, we have the trajectory of a handful authors. You can do for every authors in this, but as examples, we just pick a whole bunch of these authors to present. Okay, now let me going to show you a video here. Okay, I'm going to show you a video to see how this trajectory of these individual authors. Okay, give a minute. Okay, so here is the trajectory. Okay. Okay. So for example, you can take a look about, okay, so let's pick, okay, let's pick, okay, so let's put again, okay. Remember, this is, okay, this is Xihong Lin. Xihong did his PhD under Norman Breslow in the corner, in the sub area of general estimation equations. So you can see this red curve. This is shows like the research interest of Xihong Lin over the years from the 1990s to 2015, okay. So it sort of shows that she moved from GE a lot to this like a long parametric high dimensional data analysis in the 2000. Okay, she has actually made papers like on density selector, variable selection, and with application to biostatistics. You can also take a look, for example, Larry Wasserman. Larry Wasserman, in his early career, actually he did a lot of Bayesian. Okay, so he has a lot of citations for Bayesian, but over the years, you can see he also migrate to this high dimensional, or you make the core, okay, the center of the trend. Okay, okay, and Bing Yu may be a little surprising to you, but Bing Yu, here's the Bayesian color on the top. But so you may be surprised that Bing Yu has a lot of citation from the Bayesian side, but that is 1990s. I think she graduated somewhere in 1990, okay, from Berkeley, and in her early career, she did has a lot of citation from the Bayesian side, okay. So this is a trend. You may find that a lot of people like Bing Yu, Jun Liu, Xihong, Larry Wasserman, they all moved to the different areas to the areas in the center of the triangle, which is actually long parametric and lasso and bootstrap. You may interpret them as high dimensional data analysis in the 2010, 2015. Okay. There are other people, for example, Peter Bickel and Jianqing Fan, they do not move that much. And I think the interpretation is that they already in the most hot area, which is long parametric in the 1990s. So when they move to the 2020, they continue to work on that area. And you can also add this color to Zhiliang Yin and Dan Yulin. This is I think this is a survival and number 6 is survival and longitudinal. Okay, Cox model kind of thing. So they already in this hot area. So after a long time, they still work on this area because the genomics become really hot. Okay, from the 1990s and until 2015. Okay. So this is a trajectory. Okay, now let me, sorry for the accident, need to come back to the slides. Okay. 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 Okay, so this is a snapshot, the last snapshot of the trajectory. Okay, let's just excuse me for just give me a few more minutes to wrap up. Okay, so we have showed you research. We showed you a research statistical triangle. We have showed you a research map, which every author in this data set, the gray dot here is a represent author. And if you write all these points to a convex linear combination of the 3 vertices we estimated, that's actually represent the estimated research interest of the author. Okay, for example, you may find Bradley Efron here. So Bradley Efron, okay, you can write it as a convex linear combination of 3 vertices, and that's his weights. Okay, based on these weights, we can construct a research map. We can also compute the research trajectory. Okay, so you may not work on, you may not research currently interested in network, but if you work on other areas like long negative matrix factorization, you may work on like a single cell genetics and a text analysis. All these data set, you can treat them as count data. Okay, it's very similar to network data. It's count data. They are non-negative, and their probability matrix a lot of times also is structured rank K. So therefore, for those kind of data set, you can extend the simplex structure we find here and extend the mixed score method there. Let me use 5 more minutes to wrap up what to go over a little bit about the theory. Okay. In order to prove all this consistency, first of all, we need mild regularity conditions on the balance of the communities. Then we need to characterize the signal strengths. The signal strengths of the network is based on calibrated by the average degree and the sort of the similarity between different communities. Especially for real network, it's very important to allow the weak signals, and we use these to measure the loss. Okay. The first is the optimality result is we have for the mixed score, we estimate this pi matrix. Okay. This is the upper bound, this is the lower bound. They're almost the same if this term is constant. And in particular, if the degree the parameter are all at the same order, this is actually constant. So the lower bound and upper bound match with each other, okay, up to root log n factor. So this suggests mixed score actually is optimal if all the set i's are in the same order. Now, in more complicated situation, if all the set I is not in the same order, and this is particularly important for network. Why? Because network and other type of data like text text document data, it's very important to know that the degree, they should not be at the same order. Okay. So it takes a lot of technical effort, but we can establish upper bound and lower bound to match each other in these more complicated situations. But if the set i's are at the same order, this reduces the previous slides. Okay. But this is just extend the theory to more general setting. And the main concern here is the real data. For real data, all the set i's have to be different order. Okay. But technically not hard. Okay. Here's a figure to show the most important insight about how accurately you can estimate your pi I. For example, if my set I is 10 and the Jiashun Jin's set I is 100, so this tells different my pi I and Jiashun Jin's pi I. The base you can estimate Okay, the accuracy are different. Here's the set I. Okay, here's the set bar. Okay, in this range, the set I is very, very large. So your set I is very large. It means you have a lot of aids. So your pi can be very accurate. But you cannot estimate it infinitely accurate. Very soon, you're going to reach a flat state, like 1/10 kind of thing. Okay, so this is a flat. If your degree is very, very small, so we cannot estimate your pi at all. Okay, in that kind of case, so this is a weight vector, this is a weight vector. So that their L2 norm, the worst case is 2. Okay, so that's comparable to 1. Okay, and in between, it's very interesting. Your set I is not too large, not too small. That means we can estimate your set I not very satisfactory, but it's better than doing nothing. Okay, so this is the rate you can estimate your computed I. Okay, so putting all this together, you get this very complicated formula here, but it's sharp. You compute upper bound, lower bound. So the main technique to do this is relate your pi I hat and the pi I to the Ri hat and Ri, and this is build corresponding eigenvectors. Okay. The key is to bound this, and the main technique is use entry-wise eigenvector analysis, which is pretty advanced, pretty hard. Okay. To analyze these eigenvectors, we need to use the leave one out tricks. Okay, so a lot of people like here are using this kind of technique to analyze eigenvectors. Okay, the basic idea is this. First, for example, you take the first eigenvector and this adjacent matrix, they are correlated. Now, if you take a row of it, ith row. Okay, so this is random variable. This random variable actually can be approximated by this guy. But this guy, cosine 1 theta, is constructed by removing the ith row and ith column of A and recalculate the eigenvector, first eigenvector. So this guy turns out is independent of I multiply EI. Okay, so you create by leave one out, leave one row and a column out, you create a lot of independence, with thus make the analysis doable. Okay. Now this is a leave one out tricks. Okay, if you need to do this kind of thing, okay, this leave one out very important. Now the second question is, how is the analysis we do here different from all those papers cited here? Okay, all those papers cited here, they are more or less is on more theoretical settings. In the most theoretical settings, their set I are on the same magnitude, like the set max and set min, the same magnitude. Okay, but in order to make your theory is relevant for the application we present there, you have to deal with the more difficult situation where the set I's are at different orders. So that's the main contribution here, theoretical computation here for us on the leave one out. Okay, so I'm going to wrap up here. So we have introduced a data set, okay, which is freely available to everybody. And we have the proposed model. We have many other works on the degree corrected mixed membership model. We show that this becomes a very good model because mathematically it's still very tractable, but in applications quite realistic. Okay, we have good fit result coming up very soon. Okay. In terms of method theory, we have the score normalization. We have proved the matching upper bound and lower bound. And for the real data, we have for discover statistical triangle. We have to build a research map, and we can compute the research trajectory for authors. As long as you are one of the 2,830 authors in that cited works, we can plot the research trajectory. Okay, so here are the some references. Okay, here are the 2 data set references, and 2 papers on mixed scores, and this is a survey paper on score. Thanks for your attention. Okay.